All right, welcome everybody to a new video here on our unit covering radicals. We've talked for the first few lessons and first few videos about transformations to lay a groundwork for the rest of what we'll talk about throughout this unit. And today we're going to talk about graphs and tables and see how we can look at a graph and find a function from that, as well as how to create a table or a list of coordinate points or ordered pairs that match this function and the graph that is given. And a few miscellaneous questions will show up along the way. What I first want to start out with is looking at our parent functions that we're discussing in this unit one more time from a different context. So last lesson we looked at square roots and cube roots and then saw how we could transform those by changing a's, b's, h's, and k's, by moving the graph up and down, left and right, vertically or horizontally stretching or shrinking it and reflecting it or flipping it upside down over the x-axis or from right to left over the y-axis. So in order to get an understanding of what these transformations will look like and how we can find a function from them, we first need to know what the parent functions look like. So all the transformed functions are children. Those children come from these parents. So how I'd like to describe a square root parent function or any of its children is that the shape is kind of like a jump, right? It has a starting point and then it shoots off somewhere. So in this case, for the parent, right, not any of the transformations, but the parent always starts at the origin. And in this case, it will jump up towards the right. Now, when we transform that, things may change, as we'll see shortly. For a cube root, on the other hand, the shape of that graph is best described, I think, as an S, and the center of the S is at the origin as well. So we're going to take a look, keeping these parent functions in mind, at some graphs. But before I do, I also want to point out that we can find tables from these parent functions as well, so it's going to help us as we move on. And these tables, remember, functions are always something that you can plug a number into and get a number back from. Actually, if I bring this graph back over here quickly. If I plug 0 into x, the square root of 0 is just 0. If I plug 1 into x, the square root of 1 is 1. If I plug 4 into x, the square root of 4 is 2. These are all coordinates, x comma y, that should show up on our square root graph, and indeed they do. Look for perfect squares. When you're working with square roots, square root of 9, for example, is 3, square root of 16 is 4. Look for something that's going to allow you to find a perfect square inside your radical there. Similarly with cubes, you're looking for perfect cubes. Now this is a little bit different, right? You know your list of perfect squares maybe not perfect cubes so much. What I would recommend is that you should look for numbers that simplify inside to equal either -1 or 0 or +1. Those will always simplify to be a whole number. For example, what times what times what is -1? -1 times -1 times -1 is -1. So when x is -1, when you plug that into x and you calculate that or you simplify, y is -1 as well. If you plug 0 into x and think about what times what times what is 0, 0 times 0 times 0 is 0. And what times what would be 1? 1 times 1 times 1 would be 1. So when x is 1, y is 1. You can find other values like the cube root of 8. 2 times 2 times 2 is 8. So when x is 8, that simplifies to y being 2. That just helps you kind of get a little bit of an understanding of what tables should look like of coordinate points, x comma y. So keep those in mind, and let's go ahead and start taking a look at some transformed functions and how we can, given our knowledge of our parents, right, our parent functions, how we can create a transformed function here. So first thing we should do is think about what does this parent look more like? Does it look more like a square root or a cube root graph? And I hope that you remember that in this case we have something that looks more like a jump. Now obviously that's not the same type of jump that we had earlier for our parent, but there is a starting point and that graph does shoot off in a certain direction. In this case it's down towards the right. So the parent has to be a square root in this case. And that square root has clearly been transformed. For instance, this jump does not start at the origin anymore, right? It goes to the left by 1 and up by 3. So that's part of what I would use to describe this transformation. Left 1 unit, up 3 units. And something else that has happened if you compare this to the parent, right? The parent goes up towards the right. This one goes down towards the right. Clearly, something else that has happened here is this graph is flipped or reflected upside down, reflected over the x-axis or across the x-axis. So 3 transformations happening here. X-axis. Okay? 3 transformations happening here. All you got to do now is the same thing we did in our last video. Use these words and think about what's changed. A, B, H, or K. Change this square root to match this description. Now, of course, this should have a different name. Right? Children should have different names from their parents usually, especially since, in this case, these functions will look different. And in this case, we have a square root at the beginning. We'll have a square root at the end. A reflection over the x-axis, if you remember correctly, changes A. Right? We have a negative. Right? Reflection means negative. We have a negative in front of our parent. We move left by 1. When we move left, we change H. And we change H by adding something next to X. That goes inside of our function. Anything horizontal is inside, anything vertical is outside. And then changing K, because up by 3 means we change K. Add a number off to the side of the square root, not underneath it, plus 3. If you graph this in Desmos, okay, it's going to look different than the parent, of course, but that's good because we started with something different than the parent, right? We started with a transformed function, and this here will match what you see visually on the board. Okay, so that's for square roots. Before I move on, I do want to go ahead and touch on tables here as well. Okay, one coordinate point for this table clearly would be -1, +3. Another point that you can see visually would be 0, 2. Another point would be 3, 1. You can see this more easily, I think, on Desmos. But another way that you can calculate this is to try to plug a number into this function and then simplify and then see what you get. For example, if I plug -1 into x here, -1 plus 1 will be 0. The square root of 0 is just 0. -0 stays 0. And 0 plus 3 is 3. So when x is -1, when we plug that in, we get 3 back for y. Or if we plugged in a 0 here, 0 plus 1 is 1. The square root of 1 stays 1. -1 plus 3 is 2. So when x is 0, y will be 2. So this makes sense not just for the graph, it also makes sense for the function that we're given. This table should match both. One more example quickly. If I plug 3 into x, what do I get back for y? 3 plus 1 is 4, the square root of 4 is 2, and -2 plus 3 is 1. So that's how you can confirm and write out a list of coordinate points that, if you're graphing this by hand, would confirm that this is indeed what you have. You can also check on Desmos. So that's square roots. Cube roots, on the other hand, we can see here that the transformation, I'll go ahead and make the center of this S a little bit more clear. We start with a cube root, clearly. This is the shape of an S, just like a cube root has the shape of an S, so that's first of all. This is a cube root. And the center of this S, if you look closely, is here. Now that's at 1, I believe that's -4, so that's what you would want to write down as part of your transformation. You moved right 1 unit and down 4 units. Did you flip this S upside down or anything? No. write 1 unit down 4 units. That was the only type of transformations that you had for this parent function. Okay, so writing the transformed function should not be too difficult. All we're doing is changing h and k in this case. We remember that we should have a different name here. Okay, we should still have a cube root though, because this will look a little bit similar to our parent. There's no reflection. There's no A, there's no B, there's no vertical stretch or shrink, horizontal stretch or shrink. Instead, write by 1 unit means in this case we're going to subtract next to x inside of our cube root, inside of our radical, and we're subtracting by 1. And then we're moving down by 4, so we are subtracting off to the side by 4, we're changing k. So don't get those confused. H and k are very easy to mix up, but remember, anything horizontal happens inside of the cube root or square root, anything outside changes things vertically. Okay, so that would be how we can write a transformed function for a cube root based on what we're given from the graph. If you graph this on Desmos, once again, it will or it should give you the same picture that you're seeing here for this original graph that you started with. Okay, and that's how you know you're correct. So always write things out in words. Don't look at the coordinate point that the center of the S is. Okay, just look at and write out in words the transformation, combine that with the parent to come up with your new function. The last thing I want to return to here is a few questions that relate to a table. Okay, so we saw earlier how you can create a table. Plug a number in for x, get a number back for y, or look visually on a graph, but be careful. If you're looking visually on a graph, sometimes it's easy to make mistakes. So always take that number that you're trying or think shows up on a graph, plug it into your function. It should simplify to give you that y coordinate correctly that you should be able to see visually. Now, let's consider some other questions though. For example, what happens if we try to plug -4 into x? Well, if I try to plug -4 into x, think about what would happen. -4 plus 1 would be a -3. Okay? Square root of a negative. If you remember back to last semester when we were talking about imaginary numbers, those come with negatives under the square root. Now, do negative numbers under a square root, do imaginary numbers show up on a real number graph? The answer is no. Okay? This is actually, if you type this in the calculator, going to give you something undefined, or the calculator might say error, because the answer that comes back is not a real number, it's an imaginary number. When we're talking about this unit, we're going to be talking about real numbers. So when you type in -4, is there a graph over here? When x is -4? No, there's no graph over here. In fact, the jumping point heads that way, towards the right, not over towards the left. There is no graph over here. That's why this is undefined. Okay, that's why there's no graph. That's why there's nothing here. It's an imaginary number, not a real number. That's one thing to remember as you're going through looking for coordinate points for this table. What if we have a decimal, like 1.5? Well, something to remember in this case is that if we're going to try to plug in something like 1.5 into x, that number is in between 2 points that are already on our list of coordinate points, right? 0 and 3. 1.5 is in between those two numbers. So what does that mean? That means our return value should be between 2 and 1. If I simplify this, I'm going to get a decimal, and that decimal actually is going to be between 2 and 1 because 1.5 is in between 0 and 3. Those match, right? The input will match the output. If it's in between 0 and 3, the return value will, in this case, between these two return values we saw earlier. So we will get a decimal. That decimal will specifically be between, in this case, 1 and 2, or 2 and 1. You can check that yourself. Try to simplify this. What will you get? It will be a decimal between 1 and 2. It will be 1 point something. And lastly, Finally, what is x such that f of x equals 0? So in other words, the way to ask this would be, when y is 0, what is x? So pretend I have another table here, x comma y, and I'm looking for when the y coordinate is 0. Okay? That means that this side over here, I'm going to erase this real quick, g of x, f of x, these mean the same thing as y. So if y is 0, everything has to equal 0. Now what I could recommend you to do is to test different numbers, plug different numbers into x, see what you get back for y. In this case, that's going to turn out to be, I believe, an 8. I believe it's going to be 8 comma 0. But this is going to get us into solving, which we're going to talk about more so in a few videos from now. But what you can see here is that if you do plug in an 8, 8 plus 1 is 9. The square root of 9 is 3, and negative 3 plus 3 is 0. So when x is 8, only then is y equal to 0. That's your x-intercept as well. That jumps ahead a couple videos as well. So you could either test numbers for x, get numbers back for y, or if you wanted to, you could actually isolate x by subtracting by 3 and then dividing by a negative. That'll give you 3 equals the square root of x plus 1. And then you could square both sides. We're going to see this in a future video. Squaring both sides will give you 9 equals x plus 1, and subtracting 1 to both sides gives you 8. So that's a bit of a preview for what to expect moving forward. Just test different numbers, see which one gives you back that 0, and that's how you know what x will be. And that is a summary of how you can move from graphs to functions and then fit tables with those graphs and functions of these parents that we've been talking about and will continue to talk about moving forward.